the Internet of Things involves setting up monitors. So you can see the state of the Internet of Things right now. Hi everyone. I love being the talk before lunch because it ends in lunch, which means my talk always has a good ending to it. So hopefully you're all psyched for that. But thank you for letting me talk here today. My name is Tim Ryan. I'm a developer from the US. I lived in San Francisco for 2 years and then most recently moved to Boston. And that entire time I've been working on developer tools, specifically developer tools for Internet of Things devices, for drones, for basically any problem where a software developer would say, hey, I want to sense that or talk to that or move that around. Anything outside of the confines of what a computer or a phone can do, I've been interested in. And I know that the talk has Servo in the title, which is also the name of Mozilla's experimental web browser. And unfortunately, this is not going to talk about Servo at all, so I'm sorry for the disappointment. And I think that this is actually probably one of the first Rust talks which will involve Servo by the other definition of the name, like the hobbyist motor. So hopefully in the future, I'll make it up to you and talk about servos talking to the Servo browser or vice versa. But what I am here to talk about is how does Rust interact with hardware? How does Rust interact with circuits? So the biggest problem in hardware is I have information or there's something that I want to accomplish. How do I talk to it? And let's imagine that you have a laptop with Rust code running on it and a temperature sensor, which could very well look like this, like an embedded temperature sensor. Or you just have the idea that I want to go ahead and see what the temperature in a room is. Well, connecting the two is non-trivial. Essentially, some of these you could plug into your laptop via USB, but most likely they're talking some embedded protocol. You actually need to build a circuit up around them. And then what is a standard in Rust in order to talk to circuits? Is it just like reading to a file system? Is it like talking to a web server? A lot of software developers probably don't have an analog for what this looks like, even if they actually go out and develop with circuits, especially because Rust is primarily built around developing for laptops right now. And then let's say I even solve this problem. I have Rust code and I am talking to a sensor and this is happening at my home and I am now 3,000 miles away and I would love to know from my mobile phone what the temperature is in Boston, Massachusetts at my house. Is it really cold right now? Is my house burning down? I don't know. These would be great questions to find out. So this is the other problem, the Internet of Things, which is connectivity. And most likely, if you actually are doing circuits, you're aware of microcontrollers. You're aware of development boards. And these are the primary way you would talk to a circuit. Essentially, a microcontroller board is a breakout board with its own CPU on it. You plug it into a computer and you use that. You actually develop for that target. And that is what communicates to a device. A lot of these boards have different pins on them, basically little ports which say, okay, well, you can wire this to a circuit, and these pins do various functions. Sometimes they're specialized, sometimes not. But there are a lot of common ones which you might be familiar with. For example, at one end of the spectrum is microcontrollers. Here I have pictured a Tehsil board, which is similar to an Arduino board, and it's a microcontroller. It uses one from Freescale. It basically has 32 pins on it, which you can program. The more interesting part about this is that it may have a few hundred kilobytes of memory, if not only a few dozen kilobytes. It is a completely different programming model than what you're used to on a computer. It's probably single-threaded. You don't really have to worry about memory races because you're not really maintaining ownership of different overlapping memory spaces. It's actually just all one memory space, so you don't really need a lot of the guarantees that Rust provides you, and I'll talk about that later. But it's basically a very exotic programming model. At the other end of the spectrum, you have microprocessors. A good example of this would be the Raspberry Pi. So an embedded computer, very often it's running Linux, and it could do high-level tasks. So let's say it is running a Python science library, or maybe it is actually running a full-blown GPU. In any case, the microprocessor also has its own GPIO pins, which is to say that it can talk to a circuit. And the biggest difference between these two is that on the microcontroller side, reliability is key, predictability is key. You're doing things as fast as the processor can do them. On the microprocessor, when you're running Linux, you have a scheduler. So things are basically competing for memory, competing for time. So you can't do real-time things most often on a microprocessor when you're doing something built on like a standard Raspberry Pi distribution. So for the past few years, I've been working on a project with several other people called Tessel, and it's just another microcontroller board, but I've been excited by it because it's fully open source hardware, and for our particular example, it actually has a microprocessor and a microcontroller, so we can get the best of both worlds, or the worst of both worlds, as the case may be. Essentially, the Tessel project is, I've been working on it since 2013. Originally, it was a company, and then now it's just a open source group with a small steering committee, and which otherwise accepts open source contributions. And we designed it specifically as a platform for IoT, specifically tailored for software developers. Originally, we targeted Node.js. All of our libraries were written in Node.js, our command line tools, etc. And more recently, because Rust reached maturity with 1.0, we've been excited to say, okay, well, let's develop an environment that takes the same tool sets that Rust developers are using, Cargo, Rust-C, etc., and bring them into a microcontroller platform that's really easy. So the trajectory is we found a lot of C code, low-level C code, ported it to JavaScript, and are now porting it to Rust, each time learning the benefits of each language and like learning a lot about ourselves is like, wow, we were really young programmers back then. Another interesting thing about this is that it's an in-the-wild use of target JSON. Developing for Tessel is actually stretching the boundaries of what my knowledge is about Rust and how it cross-compiles. So it's been pretty exciting to say, okay, we'll take all the features and all the extensibility of Rust, marry it to the development environment that we've already built out, and see if we can't get the best of both worlds. So the basic hello world example is a blinking example. We want to blink some lights on and off. This is a combination of command line tools which make it really easy to get started on it and the Cargo ecosystem. So we can create a directory, we can cd into that directory. We can run t2 init and say the target language, which now is Rust. This has actually been merged in. And this will create a sample Cargo repository just like Cargo init would. We can also then run t2 run and specify the name of the Cargo toml file. And then your Tessel lights will start blinking. It'll start screaming at you that it's blinking. Please stop it if you can. But the entire point of this is that we leverage the Cargo ecosystem. We build a crate out for you. And from here on out, you can do same dependencies that you're using. You can add your own source code. You can build it into your existing system. So we really want to leverage the tools that are already there for software developers. So now that is out of the way, that is the development platform I'm talking about. Let's go back to basics. When we're talking about signals and servos, we're talking about circuits. And how many of you have circuit experience? Awesome, so that's about 50% of the room, maybe a little lower. And just to go over the basics of circuits, we're talking mostly about digital logic. Digital logic means that there are high values and there are low values, and they're being interpreted in some way. So if I have a circuit and say the voltage is 3.3, I might say that is what I declare as a high voltage. When that is high, when that signal is 3.3 volts, I want to turn a light on. And then similarly I say, oh, when the circuit is 0 volts, I want to turn the light off. And the way this works is that you can get close to 3.3, get close to 0 volts. Basically, everyone just sort of agrees that when you're close enough to these will be represented as those values. But this matches really cleanly to binary values. So a high voltage might be 1, and a low voltage might be 0. One thing about this is that you can actually look at this as a power source, not just a signal. So if I wanted to blink an LED on and off, I could just switch it from high to low. I could send out a square wave, which over time would just switch on for equal parts 3.3 volts and 0 volts. And notice that this is happening over time. So if I stretch out any of those signals, the light will be on for longer, the light will be on for a shorter amount of time. If I blink it fast enough, then it will actually be imperceptible to the human eye. But there are a lot of fun tricks you could do with that. But in Rust code, this actually maps very cleanly to what we might want to say is an imperative way of generating that same signal. So we have a few lines of setup at the beginning, which is say, okay, we want to get a port, we want to know that it's there, so we unwrap it, and we want to select pin 0. Pin 0 is going to be our LED pin. And then in a loop, we can say we want to turn the pin high, sleep for a second. We want to turn the pin low, sleep for another second. And this will generate the same signal that we just saw in the previous slide. Now note right now that this is entirely synchronous. It's actually putting the thread to sleep while we are doing this. But because we're on an embedded platform, it doesn't matter about wasting clock cycles or anything. So pins can also be inputs as well as outputs. An output pin says 0 volts or 3.3 volts. An input pin says, is this value high or low? So if I have a wire which is connected to a high voltage and then a switch in the middle, that switch is going to break the circuit. And so when I press down on a button, I'm literally saying, here's a conductive material, I'm continuing the circuit, so now I read it as a high value because we get all the way to the voltage source. And in the same way, we can say, okay, we want to turn on an LED with a switch. You could probably easily do this with a circuit, but here we're going to say, all right, there's pin 0 and pin 1, and we're going to select them and call them LED and switch. And then in our same loop, every time we read the switch, we say, is the switch on? Turn the LED on. Is switch off? Turn it low. But the extensibility here is that, well, what if I don't want to turn an LED on? What if I want to say, when the switch goes down, I make a post request to tweet that I'm home and say, hey everyone, I'm home, come hang out with me, I'm lonely, give me friends. That is also possible, and that is the magic of hardware. So not only can we do input and output, we could do complex things like sensors. And a sensor is basically a small IC or a chip which is able to talk some sort of communication protocol. And this uses the same basics as we were talking about before, input and output values. But the sensor itself, although it has a lot of different pins, including power and ground, and 2 GPIO pins, the only ones we care about are this data signal and this clock signal. These two in combination allow us to actually talk to the microcontroller and measure something about the outside world. So what does I2C look like? So those two pins, the data and the clock pin, could be wired to the protocol which is known as I2C, which is a protocol dating back like 30 years. And this is basically an agreement between the two processors about how the signal works. In the same way that your web browser, every server in the world, your smartwatch, your pacemaker, all of these understand HTTP as a common language. And even though at the root of it, HTTP is just plain text, it's sort of similar to this, where there's two signals and the way they modulate each other, that is what determines what the signal is. So on the clock line, you can see it go in a square wave, and every time it goes up, you might measure a value on the data line. Not to go too much into this, but the basic agreement here is that when the data lines go low, the processor will emit 7 clock bits saying the address. It'll say we're trying to write a bit, and then the IC, the accelerometer, will write back and say good. And then we'll write another byte over to it, and then the IC will say good again. I2C is much more complicated than this, but the key point to notice about this is that it's happening at 100 kilohertz. So if you imagine that human perception can measure about 30 hertz, 100 kilohertz is extremely fast, and this can go all the way up to 1 megahertz, 4 megahertz. Your PC is probably running RAM at 233 megahertz or higher. So these are really, really high speeds. And not only are they hard for us to think about, it's probably too fast for Rust to do. And I specifically mean that when you're trying to do these communication protocols, you're not just going to be sitting there flipping a switch on and off in order to say what the sensor should read. It's actually going to be handled by something much lower level. Hardware controllers exist in every piece of software. They exist in your USB controllers, the way your laptop talks to your LCD screen. And we're just going to tell the hardware what to do and say, these are the registers we want written to. Do some black magic, and then give us a result, whether it's the input that we want to read or the output. So what do we do when we have a low-level protocol that we want to wrap in a high-level system? We write an API for it. And so here's that same example of here's an accelerometer, and how do we write to it? This is using all the lowest level primitives that we want. And skipping down to it, we first do a transfer to the address 0x1d. We say, you are the accelerometer, I'm going to write a 0xd to you. Can you please send me back the register value at that? 0xd means who am I? It responds with 0x2a. By agreement, we just say, okay, well this is our handshake value. We know we're talking to an accelerometer. Great. And then in the next line, we can say another transfer, read register 0x01, read back 6 bytes into this mutable buffer. And then we parse over it using some data, using some logic that was specified in the data sheet. But what it boils down to is we now have a tuple of 3D acceleration vectors. Depending on which way we angle the accelerometer value, we will get different values here. And that was just 14 lines of code to pick up an arbitrary IC that we found on Adafruit or SparkFun and start talking to it in Rust. And of course, you might look at that and you say, well, that's pretty ugly, so let's publish a crate around it. And let's make it nicer with human terms, like create an accelerometer, expect that it is actually connected to us, and read the acceleration. And you could go to crates.io right now and download this accelerometer crate if you want to talk to it. So one key thing about Rust here is that we actually have a very strong advantage of using Rust over any other system language that I've used, especially over using JavaScript in this case, where let's imagine I was trying to write to the same thing at the same time. I have an LED and I want to send it high or low, but I also have the I2C port, so I want to send its signals. With Rust, we can actually say these are mutually exclusive. You can't mutate both at the same time. So when we have an I2C port, we can write some data, and then if we want to accidentally send a high value because we want to turn an LED on, but we do it on the wrong pin, we can say Rust can prevent us from doing this. And then we can go out of scope, and we can say, okay, we're good, you can go ahead and write to that pin. But basically, it creates very fault-tolerant systems well before actually we have to run any code on the device. And if there's anything more harrowing than trying to figure out why something's going wrong on your computer, it's probably trying to figure out why something's going wrong in a circuit. So this has been a huge boon when designing this API. So basically, in designing this, we realized that Rust provides these high-level type-safe abstractions for things we've been doing for years, and it allows us to do it in a way that makes it really approachable, where it's like, really you would want to encourage anyone to be able to talk to an arbitrary IC, to be able to do circuit-level logic, because it isn't too different from software development. And this harkens back to a quote that I read from Rust Camp last year, by team member Aaron Turin, where he said, do programming in places you're afraid to do it before. And hardware and electrical development literally is one of these places that I was afraid to do it before I picked it up. And with anyone that I've worked in a workshop with has been like excited at the end of it, never expecting they would be able to do that. But another way of phrasing this is hack without fear. This was also the quote that they used last year to sort of summarize the Rust methodology. And so I went ahead and actually started hacking away at things, power cords in my house, in order to make a few demos. So here's a power cord which has the wires stripped on the left. You can see those 2 leads pointing out. So you definitely shouldn't plug this in and touch them both at the same time or either of them, but they do plug into a circuit really well. And on the right here is a warning that I actually stripped off of the power strip saying, specifically don't do this. So given that there are no more warnings, we can go ahead and we can produce a demo. So over the past, pretty much the past 2 weeks, we went shopping, we bought a bunch of sensors, and we came up with 5 different crates that exemplify different sort of sensors, Bluetooth Low Energy, climate sensor, relay, and servo. And so for this first example, I want to go back to the accelerometer demo and say, I want to check the temperature of our home. If it's too hot, I want to be able to turn on the air conditioner. And so for this, I'm going to pick up the 2 crates, the temperature sensor. The climate sensor is actually both a temperature and humidity sensor, but we only have to use one of them for now. And then for the other one, I want to say, pick a relay. A relay is basically a very high-powered switch, and you write to it either saying high to turn on the switch or low to turn off the switch. But it can handle large voltages at one end without damaging your tiny little microcontroller. So in this video, I'm basically using a web server that is hosted on the Tessel, and I'm going to go ahead and hit the start cooling button, which will turn on the relay and thus turn on the fan in the background. And so you can see the temperature slowly dropping because of the climate sensor, which is right there inside of the Tessel itself. Oh. There we go. But you believe me anyway. So yeah, so we are actually reading live temperature data. And you can imagine if I was a mile away or, again, in Berlin, and actually trying to measure this at my house, I want to be able to go home, turn on the air conditioner 30 minutes before I arrive, and be able to do this. So a very simple example using a microcontroller and a few sensors. The next one I want to show you is an actual use of the servo. So a servo is a hobby motor that can turn from 0 to 180 degrees. And the best part about a servo is that it can turn to a fixed point. So unlike a motor where you're just saying, okay, go forward or go backward at a certain speed, servos can have specific positions on them. And this one is actually very similar to the demo that we saw earlier today, where it's turn on a light automatically when you walk into a room. This can also scale to, I want to unlock my door when I approach my door, which should sound familiar. But we're going to start with the servo crate and a Bluetooth low energy module and do a low quality version of this demo. So as I approach the front door, a sensor inside is reading Bluetooth IDs. And the servo right here is mapped to turn the light switch on when it detects the Bluetooth ID of my phone, as I look proudly over my domain. So anyway, that took 20 lines of code, and that took 20 lines of code, and that was just an example of, okay, entirely Rust code running on something embedded that is doing things with sensors and servos that is very applicable to our daily lives. Like, we are developing companies around these IoT concepts. We are buying new products around these IoT concepts. And so in true Rust fashion, we have to ask ourselves, are we IoT yet? Is Rust ready for the Internet of Things? And I don't want to give a definitive answer on that because I am just a developer. And only one developer, and there is a room full of you. So I want you to ponder some of these problems in IoT that we have right now. If the three biggest things that I know of that I consider problems are security, reliability, and power. A few years ago, we had the shell shock bug, if I'm not mistaken, was the bug that allowed you to do a buffer overrun in a router. So essentially, if you sent a malformed HTTP header to a router, it would run past the buffer that it allocated for that, and you could get remote code execution on it. Now, remote code execution isn't a big deal itself, but the idea that you have a router in your home, in millions of homes, and you can't update those, well, that's a huge deal. And when they can't be updated, you really have to get security right the first time by making sure you have all these guarantees. It happens at the OS level in SCL4 Linux, in AppArmor, in all these different layers, but Rust is really like the final defense for what input goes into your program and what you're going to be able to do. The second one is reliability, and I don't mean this in the way that like my Bluetooth is suddenly not working or my app crashed randomly. Reliability really is that we are going to continue to build and rely on these different devices to control our locks, to control our food, to control our security, to protect our children, to protect us while we're driving cars. Like, technology is eating so many components of our lives. And I think IoT sometimes gets a bad rap because essentially we're just seeing these systems at the fringes. We're seeing it how easily they break. Even though every system has its own frailty, when you do these sort of low and these embedded systems and these creative applications of it, you really see that a lot more. So when we're talking about explicit error handling or memory safety, or even the ability to not have your program crash at random, like, the extreme of this is that one day this might actually save a life to do protective coding. But even then, it will save you time and save you money if you're not debugging these things. So Rust is a worthwhile investment. And the last one would be power. And I think this is funny because we talk about zero-cost allocations, and these are hugely important when you're doing benchmarks, but it's very important when all you have is like a few kilobytes of memory to spare. And I think when Julia Evans said at the end of RustConf, how Rust is making a new generation of systems developers, well, if there's going to be a new generation of IoT developers, then they're going to run into these problems too. And it makes it easier when we have the choice between zero-cost allocation or using the abstractions you want. Because most commonly in an embedded scenario, it's a choice between zero-cost abstraction or doing it completely unsafely and hoping it works. So I'm going to leave us off with not some problems with the Rust ecosystem, but with some goals. Essentially, cross-compilation has been like a gold standard for Rust right now. The standard lib is compatible across Linux, OS X, and Windows. We also have Mayo, which sort of sets the baseline for working on all these different operating systems. So if you imagine you're writing a library, having cross-compilation capability or working across these different platforms is extreme nice to have. But there's also more platforms than that. And as Rust keeps being brought to more and more systems, as it becomes more popular, we really should think about, okay, well, what is it going to be this constant trek uphill trying to support all these systems? Is it something we can maintain? Is it something that's overbearing? Can we make it easier for developers on different platforms to debug, to compile, to actually program for these in the same way that Rust Up makes it for Rust today? And the second question is, can we have a goal of combining real-time and non-real-time systems? And basically, what this boils down to for embedded is, can we combine synchronous and asynchronous systems? Built onto Tokyo, the project is asynchronous systems that make doing zero allocation zero allocation event loops on computers possible, which is an amazing boon for anyone writing high-performance code. But if you look at a low embedded system, you may not even have the option to use threads. So as we're going forward, can we balance this idea of having asynchronous systems for high performance, but also being able to target low-power embedded platforms and still offer them something convenient out of the Rust standard library? And last, there were a lot of goals for Rust in 2017. I think another one would be to see Rust at its lowest level. There's a lot of embedded OS projects in Rust right now, including Zinc, including Talk. There's also a whole slew of PC OSs coming out. And there are hardware projects in Rust specifically designed to do what I just demonstrated today, to talk to circuits. There's sysfs, which is available on Linux and Raspberry Pi. There's serial.rs for doing hobby robotics or talking to Arduinos. There's Tessel Rust, and there's more. In the sensor libraries that I wrote today currently only work on one platform. Going forward, can we design a foundation that brings all these different things together? And if we're able to do that, then I think Rust, where previously we would pick C++ for robotics, C for embedded systems, and maybe JavaScript for internet-connected systems like servers and browsers, we might see Rust fill all of these niches in a very compatible way and actually make Rust one of the premier languages of the Internet of Things. And that would be an amazing goal for me, and I hope you share that idea. Thank you very much for letting me talk today. You can see any of the code demos at RustFest 2016. You can see what I'm currently working on at Tessel/Tessel Rust, and go enjoy your lunch.